So yesterday we were doing some curve sketching stuff. We will pick it up here. We'll talk about limits quickly. So let's start with an easy one. So this is the question. It says, evaluate the limit for this function. Now, usually the first thing you want to do is you want to plug and chug. You just want to plug, where's my pen? Just give me a second. All right, I'm back. So this is a function. It's a rational function. Probably looks something like this. The question is, at x goes to positive infinity. I don't know if it looks like this. It could also be something like this. At x goes to positive infinity over here. When x is positive infinity, what is the y value? That's the question. What is it approaching? So the step number one for solving any limit problems, what we do is we straight up plug and chug. We will just plug the number in there and see what we would get, okay? So here, let's plug infinity in there. This is gonna sound stupid, but we're just gonna plug infinity in there. So let's say 2 times infinity minus 3 over infinity plus 1. Infinity times anything is infinity. Infinity take away 3 does not impact infinity at all. Infinity plus 1 is infinity. And now what is infinity over infinity? It is most certainly not 1. You cannot cancel out infinity over infinities. This is what we call an indeterminate or undefined form. Indeterminate form. This we cannot evaluate. So that is the technical answer, but we can do better. That's not the correct answer. Plug and chug very, very, very rarely works. So what we're gonna do here is that we're gonna think a little bit. We cannot have infinity over infinity. This is what we don't want. So that means we cannot just plug infinity in there. So we have to think a little bit, and this is the technique. If you get an indeterminate form, what you do is you want to divide, okay? You want to divide every expression in there, every term in there, okay? Inside the function with the highest power of x, with the highest degree of x in the entire function. What's the degree of x in the numerator? What's the degree of x in the denominator? 1. So what we do is equals to limit as x approaches positive infinity, we are gonna divide every term in there with x. So 2x over x minus 3 over x, like that. Same thing in the denominator. X over x plus 1 over x. Why do we do this? Because x's cancel out here, which will give us a little bit of a better idea of what's going on. So this x and this x cancels out. So what are we left with? Limit as x approaches positive infinity. 2x over x is 2 minus 3 over x. 1 plus 1 over x, like that, okay? Now what? Now you want to think. Let's look at these two terms, 3 over x and 1 over x. If you divide 3 by a huge number, 10 trillion, billion, whatever. In other words, if you divide 3 by infinity, what do you get? If you divide 3 by a very, very, very large number, approximately what do you get? 0, okay? You'll get 0.000 something. Approximately, it'll be 0. Anytime you divide by infinity, the answer is approaching 0. The limit is approaching 0. So what this means is when we plug infinity in here and in here as x, because those are the only x's remaining, we will get 2 minus 0 on the numerator, and we'll get 1 plus 0 in the denominator, which will give us 2 in the numerator. It'll give us 1 in the denominator. The answer is 2. So when x approaches positive infinity for this function, the y value will be approaching 2. And we can double check our answer here by graphing it. So 2x minus 3 divided by x plus 1. So this is what the graph looks like. Let's zoom all the way out to like infinity. Infinity means what here? We don't even know. But as you can see, as the x value becomes larger and larger and larger, what's the y value? 2, right? So that's what the limit is. That's what we found here. That 2 is that y value. So what do you want to do? You want to divide by the highest power of x, okay? By the highest power of x. Here, let's look at the next question. Same thing's going to happen here. If you plug infinity in there, you're going to get infinity over infinity, which is indeterminate form. We don't want that. So what we do is we divide by the highest power of x. In this entire function, what's the highest power of x? It's x squared. So limit as x approaches, now we're looking at negative infinity, we're looking at this side. So we do x over x squared all over x squared over x squared plus 1 over x squared. So this will give us limit as x approaches negative infinity of 1 over x all over 1 plus 1 over x squared. So that is what we have right now. Remember, 1 over x approaches what? Whenever you divide by infinity, what does it approach? 0. What about when you divide by infinity squared? What does it approach? Same idea, 0. 1 over infinity or 1 over infinity squared, both of them will approach 0. So here, when you plug in the negative infinities there, 1 over a very, very big negative number, so 1 over negative 10 trillion or something, that would be approximately 0 on the numerator. We have a 1 here, so 1 plus 1 over infinity squared. So 1 over this squared will approach 0 as well. So 0. So you get 0 over a 1, which is a 0. Therefore, this one at negative infinity, the y value will approach 0. And we can double check. So it's x over x squared plus 1. So x over, let's see, x over x squared plus 1. And we're predicting at negative infinity, the y value will approach 0. So we go to a very big negative number. You'll see when you follow this line, it's going to become negative 0.001, and it becomes 0 here, okay? So that's the idea. C is the same thing. And now we are going to use a shortcut method, right? The biggest power here is what? It's x squared. So we're going to divide every term in here by x squared. So 2x squared over x squared, this cancels out. 3x squared over x squared, this cancels out. X over x squared, you're left with 1 over x. And then you have this over x squared, you have this over x squared. 3 divided by infinity squared is a 0, so this goes away. 4 divided by an infinity squared is a 0, so this goes away. 1 divided by a very large number, 1 over infinity is a 0, so this goes away. Therefore, the solution to this is going to be 2 over 3, and that's it. Final answer. Did that make sense? Determine the equation of, sorry, not the equation. Yeah, it is. Equation of horizontal asymptotes. So it's the same concept as the previous question. So this is how you find the horizontal asymptote. You're gonna do limit as x goes to positive or negative infinity of this function, 3x plus 5 over 2x minus 1. Horizontal asymptotes, you kind of have to check it on both ends, okay? What do we divide this by? What's the biggest power of x? It's x power 1, okay? It's x power 1. So we're going to do 3x over x plus 5 over x over 2x over x minus 1 over x. This and this cancels out. This and this cancels out. 5 over a big number, 0. 1 over a big number, 0. So the asymptote here is 3 over 2. Here's a shortcut for this. If the degree in the numerator is equals to the degree in the denominator, the horizontal asymptote will be the leading coefficient of numerator divided by the leading coefficient of denominator. So here this will be 3 over 2. So that's a shortcut, and that's what we found here, 3 over 2. Cool? So we know it has a horizontal asymptote at 3 over 2. What else do we know about this? Does it have a vertical asymptote? Remember, vertical asymptote is when the denominator is 0. What do you think? For which value of x is the denominator of 0? One over 2, okay? 1 over 2. You want to set the denominator equal to 0. And you'll see that when x is 1 over 2, you'll get a 0 in the denominator. So your asymptote is somewhere here, 1 over 2. And this here is 3 over 2. And that here is 1 over 2. Now the question says whether it approaches from above or below. So there's only two possibilities here. Either your graph looks like this, or it looks like this. That's one possibility. The other possibility is you have 1 here, you have 1 here, okay? So what I'm going to do is I'm going to find f of 1. I want to know over here, am I above the asymptote or am I below the asymptote? So f of 1 is 3 plus 5 over 1. So that's 8. F of 1 is over here, so that means I'm here. And I can also do f of 0. So I know whether I'm above the asymptote or below the asymptote. F of 0 is going to be -5. You can plug this in a calculator. F of 0 is -5. So the only way this sketch will work is if we come from down here, go that way, and if we come from up here and go this way, because it has to write the asymptotes. So the asymptote to the right of the vertical asymptote, it approaches from above. It's approaching the horizontal asymptote from above, over here, to the right of the vertical asymptote. And to the left of the vertical asymptote, this part, is it approaching from above or below? Below, okay? Below. And there you go, that's the answer to this question. All right, here. Remember this is a shortcut for horizontal asymptotes. For horizontal asymptotes, if the degree in the numerator is less than the degree in the denominator, then you'll have a horizontal asymptote at y equals 0, okay? So for this, is the degree in the numerator less than or more than the degree in the denominator?
Less.
Less. So where's the horizontal asymptote?
At 0.
On the x-axis at y equals 0, yes. So we know this function has this here at y equals 0. Here's another way to find that, right? That's the shortcut. Sometimes the teachers want you to show the steps. So if you want the steps, what we do is limit as x approaches infinity of 3x over x squared minus x minus 6. And you want to divide by the biggest power. So the biggest power here is x squared. And you'll see that this becomes a 0, this becomes a 0, this becomes a 0, this becomes a 1. So you have 0 over 1, 0. That's how we get this. The shortcut comes from the fact that we're using the limit to evaluate the answer. So that would be your step. You just divide everything by x squared, cancel out the x squared, and whatever's left is 0. What about the vertical asymptotes? How do we find the vertical asymptotes? What do we set equal to 0? So for vertical asymptotes, you want to set denominator equal to 0, okay? So x squared minus x minus 6, let's man this. Multiplies to negative 6, adds to negative 1. What are the two numbers? Negative 3, positive 2, right? This means x is 3 and x is negative 2. So you have two different vertical asymptotes. At 3, 1, 2, 3, and at negative 2, so negative 2. You can also find the x and the y-intercepts. It's very easy. To find the x-intercept, set y equal to 0. So 0 is equals to 3x over x squared minus x minus 6. We need to get rid of the denominator. How do we get rid of the denominator? We're trying to solve this for x. The step would be to get rid of the denominator. You multiply both sides by the denominator. So you multiply both sides by the denominator. On this side, it cancels out. On the other side, 0 times this is still a 0. So essentially, the denominator completely evaporates. It disappears. So you're left with this. So where's our x-intercept? At 0, right? So our function goes through 0. Sometimes in a question like this, you can cross the horizontal asymptote. You'll never cross the vertical asymptote, but horizontal asymptotes are sometimes crossable if you have an x-intercept. So this is going to be a question where the horizontal asymptote, we have to cross this because there is a 0 at x equals 0. To find the y-intercept, you want to set x equal to 0. You'll also get a 0. So this is what we have. All right. So now let's sketch this. To sketch this, you have to plug in some values. So this was 3, this was negative 2, that was a 0. I'm going to plug f of negative 3 in a calculator. I want to see what happens here. Are we above the asymptote? Are we less than the asymptote? So I'm going to plug negative 3 as my value, and I get negative 1.5. So that means at negative 3, I'm negative 1.5. It must look like this. There's no zeros. It cannot cross the asymptote, okay? I'm going to do the same thing on the other side. F of 4, I'm going to plug 4 in there. So that's 12 divided by 16 minus 4 minus 6. So that's 2. F of 4 is 2. So I'm above the y-axis. I'm here. Now the only way this is going to work with respect to the two asymptotes is if you write it this way. And for the middle, you have to plug f of negative 1, and you have to plug f of 1. So f of negative 1 is negative 3 divided by 1 plus 1 minus 6. So that's 0.75. So at -1, I'm over here. The only way that's going to make sense is if it writes through that asymptote, comes here and then comes here. And then I'm going to check for f of 1. 3 divided by 1 minus 1 minus 6, I get a negative number. So that means at 1 I have a negative number, and this is the sketch of the graph. Let's talk about end behaviors. As x goes to positive infinity, where's y going? What is it approaching? Over here, what's y approaching?
Positive.
It's approaching 0, okay? Because you'll ride this asymptote to infinity forever and ever and ever. It's approaching 0. Is it approaching a 0 from below or above?
Above.
Above. So 0 from above. I think that's what they want. 0 from above. What about on the other side? As x goes to negative infinity, where's y going? Again, you follow this line and this asymptote perpetually to infinity. What value is y approaching? 0. From above or below?
From below.
Below. There we go. That's the answer to this question. So that's how you can sketch something complicated like this. Vertical asymptote, horizontal asymptote, x, y intercepts, and a couple of points. Let's look at this one. This is the third case. The first case was when they're equal. The second case is when the degree in the numerator is less than the degree in the denominator. This is the last case where the degree in the numerator happens to be bigger than the degree in the denominator. So let's first find the asymptotes. I don't know, I forgot what the question was. Find the asymptote is the question. So to find horizontal asymptotes, we do limit as x approaches infinity of this function. If you plug x as infinity right now, you would get infinity over an infinity. So that's no good. You cannot do that. So we need to do some maths. It's the same thing that we did before. You divide by the highest power of x. Every term needs to be divided by the highest degree of x. What's the highest power of x here?
X squared.
X squared. So we have 2 x squared over x squared, 3x squared over x squared, minus 1 over x squared, x over x squared, 1 over x squared. So this gives us limit as x approaches infinity of 2 plus 3 over x minus 1 over x squared all over 1 over x plus 1 over x squared. Like that, okay? What's 3 over infinity? 0. 0. What's 1 over infinity squared? 1 divided by a very, very big number. 0, right? 1 over x. What's 1 over infinity?
0.
0. 1 over x squared. What's that?
0.
0. Now look at what happens here. We have 2 plus 0 plus 0 over 0 plus 0. 2 over 0. What is that? Can we evaluate 2 over 0? No, we cannot. So what does this mean for us? This means there is no horizontal asymptote. And that's the last case. If the degree in the numerator is bigger than the degree in the denominator, okay, then you don't have a horizontal asymptote. Instead of a horizontal asymptote, what we have, if this is the case, we have something called an oblique asymptote. Oblique just means diagonal asymptote. So instead of having something like this and something like this, we'll see vertical asymptote. I don't know about the vertical asymptote, but oblique asymptotes are always like this, like that, like that, like this, like this. It's a straight line somewhere. So your graph would end up looking like, let's say you have this, let's say you have this. That's your vertical asymptote. This is your oblique asymptote. This diagonal thing is your oblique asymptote. This straight thing is your vertical asymptote. Your sketch would look something like this. So let's go back to this question. We know this one doesn't have a horizontal asymptote. What about a vertical asymptote? Vertical asymptote is when the denominator is 0. For which value of x is the denominator going to be a 0? For -1, okay?
Mm-hmm.
For -1. So we know, actually, I think usually you want to factor it, but I don't think the numerator is factorable. Multiplies to -2 adds to 3. No, it's not. So you want to factor just in case this cancels out with this, which would make our life easier. But here, this numerator, you can't man this. The numbers don't exist. So we know the vertical asymptote is at x equals -1. Now let's work on finding the oblique asymptote. For oblique asymptote, you have to do long division or you have to do synthetic division. Synthetic division you can only do when the denominator is a linear function. So the denominator here is a linear function. We can do synthetic division to find the oblique asymptote. So x plus 1, you set it equal to 0. This will give you x equals -1. That's going to be your divisor, -1. The coefficients from here come here. So 2, 3, -1. When you're doing synthetic division, the first number here always comes down as it is 2. For the next number, you would multiply 2 times -1, -2. In synthetic division, we always add. So 3 plus -2, +1. And then again, you multiply. 1 times -1 is -1. We add them up, that gives us -2. We had a quadratic, we had a degree 2 polynomial. We divided it by a linear function. What's the degree of our dividend here? What's the degree of our quotient? This is called the quotient. We had x squared. We divided this by a linear function. What's the power we get? X. So this here is a linear function, which means our quotient is 2x plus 1. This is our oblique asymptote. Okay?
Mm-hmm.
So our oblique asymptote is at 2x plus 1. So now let's sketch what we have. I think it was just asking us for the asymptotes, but we're going to go ahead and sketch this. X equals -1. So there's a vertical asymptote here at -1. And then we have an oblique asymptote at 2x plus 1. Remember how to graph a linear function. Plus 1 is there, up 2 units, across 1 units. So this is going to be my oblique asymptote. 2x plus 1. Cool?
Mm-hmm.
So when you have oblique asymptotes, usually you have things here and here. So for this, I'm going to just plug in some values. So what's a value I can plug in? Remember, this was -1. This is 0, the origin. What value of x should I plug in to determine if I'm over here or if I'm over here? What about 0.5? Or even 1. Let's just plug in 1. I want to see, my goal right now is I want to see whether I'm here below this asymptote, okay?
Mm-hmm.
Or if I'm over here above that asymptote. If I'm up there, then the shape will be like this. If I'm down here, then the shape will be like this, okay?
Mm-hmm.
So I'm just going to plug 1 in there. So let's plug 1 in there. So that gives me 2 plus 3 minus 1 over 2. 5 minus 1, 4 over 2. That's a 2. So at 1, my y value is 2, which is here. Cool?
Mm-hmm.
2x plus 1, 1. Cool. So that means my sketch must follow the asymptotes. Can only cross a horizontal asymptote. It cannot cross a vertical asymptote. So that's what I have on this side. I'm just going to quickly check for f of negative 2. I want to see if I'm here, here, or here. So I'm going to plug f of negative 2 in there, which gives me 2 times 4 plus 3 times negative 2 minus 1 divided by negative 2 plus 1 gives me negative 1. So at negative 2, I'm at negative 1, like that. So that means my function must look something like this. It must ride the asymptotes, right? So something like that. And there you go. That's the sketch. Did that make sense?
Mm-hmm.
So 3 types of asymptotes. Horizontal asymptotes, you want to find the limit, and there's a shortcut as well. Vertical asymptote, you want to set the denominator equal to 0. For oblique asymptotes, it's only going to exist if the degree in the numerator is greater than the degree in the denominator. And then you have to do long division or synthetic division. Synthetic is always quicker. If you have a linear divisor like we did here, if the denominator is linear, do synthetic division. And this is the sketch, and that's approximately what we have, yeah?
Mm-hmm.
So that's how you sketch something weird like this. Let's keep going. They used long division, which also works, right? It's not that it doesn't work, but synthetic is just better. All right, let's work on graphing these. So the question is basically graph these. I'm going to graph this as precisely as we can. Can you tell me straight up where the horizontal asymptote is going to be just by looking at this? There are 3 conditions for a horizontal asymptote. If the degree same, then it's going to be at the leading coefficient of the numerator over the leading coefficient of the denominator. If the degree in the numerator is less, then it's going to be at y equals 0. If the degree in the numerator is higher, or if it's more, then you have no HA, you have to do long division. So what's our horizontal asymptote here?
2.
2. So y equals 2. What about vertical asymptote? Vertical asymptote, you always said denominator equals 0. What value of x in that denominator will give us a 0 in the denominator?
1.
1. So you have vertical asymptote at x equals 1. X-intercept, you set the y equal to 0. Look at this, it's easier than you think. 2x plus 3 over x minus 1. How do we get rid of this denominator? You multiply. So x is going to be negative 3 over 2. Y-intercept, you want to set all the x's equal to 0. So here it'll be 3 over negative 1, negative 3. So now we have everything we need. And if you have the x-intercept, the y-intercept, those are going to be your reference points. That will give you the answer most of the time. So we have a asymptote here at y equals 2. We have an asymptote at x equals 1. Our x-intercept is negative 3 over 2, so that's 1.5 here. Our y-intercept is negative 3, so that's down here. Now look at this. There is only one way this graph can work. And that is if it comes from down here, right?
Mm-hmm.
Goes here and then goes this way. And usually if you have something down here, you have something up here, but you can check. Remember, this is 1. What value of x should I put into the function to check whether if I'm up here or if I'm down here? Anything more than 1, basically 2. 2 would do it, okay? At 2, I'm gonna find f of 2. So f of 2 is gonna be 4 plus 3 over 2 minus 1. That's 7 over 1, that's a 7. So at 2, I'm somewhere over here, okay?
Mm-hmm.
So the only way that's gonna work is if you have something like that. And that's it. Did that make sense?
Yeah.
You want to remember this. It'll save you a lot of time. Let's see what else we can do. Okay, let's do this. For this one, where is the horizontal asymptote? The degree in the numerator is bigger than the degree in the denominator. Where is the horizontal asymptote? Is there one, or is there an oblique asymptote?
Okay.
It's oblique. You would think so, right? But remember, always factor some things out, because if you can cancel the denominator, it'll make our life easier. Let's man the numerator. Why don't you tell me? When you man the numerator, what do you get? Two numbers that multiply to -6 and add to -1. What are they?
-3 and 2.
-3 and +2. Can we cancel out the x minus 3's?
Yeah.
Yes. So look at this. Your function is actually x plus 2. So here's a trick. Note, always simplify things if possible. We couldn't simplify any questions prior to this today. If you cancel some things out, like we did here, okay? If you cancel some things out like this, there will be a hole. There will be a hole in the curve, in the graph. There will be a hole. So we cancel out x minus 3, right?
Mm-hmm.
So at x equals to 3, again, set it equal to 0. At x equals to 3, there will be a hole. And the y value of that hole, you want to plug this x value into whatever function you have left. So the y value of that hole is going to be 3 plus 2 equals 5. So at 3, 5, there will be a hole. Be a hole. So what does this curve look like? So hole is when some things cancel out. So our function, our leftover function after we canceled everything, is x plus 2. Plus 2 is here. Slope is 1, so above 1, across 1. So this is our curve. If I can sketch we like that, and then we like this. There we go. So that is our y, okay? But because we canceled things out at 3, 5, so at 1, 2, 3, 1, 2, 3, 4, 5. You see this point right here? That point will not exist. There will be instead a hole like that. And there you go. That's the answer to this question. There is no vertical asymptote. There are no horizontal or oblique asymptotes, but there is a hole because when we factored, things canceled out. Let's graph this. I'm going to graph y. I'm not going to graph x plus 2. You always graph the original function. If you graph the leftover function, it's not going to show you where the hole is. So divided by x minus 3. So this is what it gave me. And our prediction was what? At the x value of 3, right? 1, 2, 3. Please let me look at that. It says undefined, right?
Mhm.
The y value is undefined. You see that hole there? How it turns into an open circle at exactly 3? I don't know why they make it so difficult, man. Just let me hold it. Yeah, there we go. You see how it changed colors?
Mhm.
It's now an open circle, whereas before, everywhere else on this graph, it's a closed circle, except at exactly 3, it's an open circle, because there is a hole in the curve at that x value. And that's going to be the case if you cancel things out. Okay, how hard does this get? What about this one? You tell me if we can factor the numerator or not. Just tell me if the numerator is factorable or not. Can we man that numerator? That's the only question right now. And we'll go from there. It's a yes or no question. Can we or can we not factor that numerator? It's a quadratic.
Yeah.
No, why not? It's because it multiplies to negative 21. Remember, when you're trying to do man, right? When you do man, it always multiplies to a times c, the coefficient of your degree term times the y-intercept. So we're looking for a number that multiplies to negative 1 and adds to negative 8. The only thing that multiplies to negative 1 is 7 and 3 and 21 and 1. Those are the only factors of 21. There is no way any combination of plus minus these guys will ever add up to negative 8. So you cannot factor this, okay? You cannot factor that numerator. So there's no hole in the curve, basically. That's what it is. Even if you could factor it, unless things canceled out, there's no hole. There's only going to be a hole if things cancel out. So this one is not even factorable. Let's not even worry about it. Where is the vertical asymptote? For what value of x is the denominator a 0?
4.
4. Is there a horizontal asymptote? No. Why? Because the degree in the numerator is bigger than the degree in the denominator. If the numerator is bigger, no horizontal asymptote. So horizontal asymptote, NA, not applicable, or you can even erase this, not even write this down. Does it have an oblique asymptote? Yes, it does. If it doesn't have a horizontal asymptote, it must have an oblique asymptote. How do we find oblique asymptotes? You do long division or you do synthetic division. Just for practice purposes, I'm going to do long division for this question, and I'll show you how to do synthetic division. So long division will always work. The thing is, right, sometimes they will give you something like this. If this was the case, notice how the denominator now is a quadratic. It's not a linear function. Cannot do synthetic. You can only do synthetic if the denominator is linear. So you need to know how to do the long division way as well. So in a long division method, we call this the divisor. We always put it outside. We call the numerator the dividend. We always put it inside and make sure all the powers are accounted for. Let's say there was no 8x term. you would put plus 0x in here if there was no 8x term. It has to be in descending order. But here, all the terms are accounted for in descending order, so we're good. Now ask yourself, what do I multiply by x to get 3x squared? What do I multiply x with to get 3x squared?
Yeah.
3x. So now x times 3x is 3x squared. Negative 4 times 3x is negative 12x. And then you have to add them up. Sorry, not add them up. Add is in synthetic, you have to subtract them. In long division, you have to subtract them. 3x squared minus 3x squared, 0. Negative 8x minus minus becomes negative 8x plus 12x becomes 4x. Once you cancel something out, you're allowed to bring the next term down. What do I multiply x by to get 4x?
4.
4. So 3x plus 4, you can stop right here. We don't care about remainders when we're looking for synthetic, when we're looking for oblique asymptotes. So that's the long division method. Synthetic division, you set the denominator equal to 0, you'll get a 4. You pull that outside. Inside, you put up the coefficients. 3, negative 8, negative 7. And if there's any x missing, you would put that as a 0. In a synthetic division, this number here always comes down as it is. What goes here? You multiply diagonally, okay? Like this, 12. Do we add or subtract? In synthetic division, do we add or subtract? We add. So plus. Negative 8 plus 12 is a 4. 4 times 4 is a 16. Negative 7 plus 16 is what? 16 minus 7 is a 9, right?
Mm-hmm.
This is your remainder. We don't care about remainders when we're looking for oblique asymptotes. This is our quotient. We had an x squared. We divided by x. That means the power of this is x. But x power 1, that means the power of this is x power 0 or no x. There we go. That is the oblique asymptote, 3x plus 4. You can use either approach for this question because the divisor was linear, okay?
Mm-hmm.
Okay, why don't you tell me something easy? What's the y-intercept for this question? To find the y-intercept, you set all the x's as 0. So what's the y-intercept? This cancels out, right? This cancels out. 8 times 0 is a 0. This cancels out. 0 is x is a 0. So the only thing you're left with is negative 7 over negative 4, yeah? Which is 7 over 4, which I think is 1.75. Let me plug that in. 7 over 4. Yeah. So that's our y-intercept. And to find the x-intercept, you set y equal to 0. So for here, we are going to do 3x squared minus 8x minus 7 equal to 0. Since we couldn't man this, you have to use the quadratic formula. That's the only way to get x-intercepts if they exist. And this is the quadratic formula. This is your a value. Negative 8 is your b value. Negative 7 is your c value. So this becomes 8. Negative 8 becomes positive 8. Plus minus b squared, so 8 squared. It's negative 8 squared technically, but since we're squaring it, the negative is going to go away anyways. Minus 4 times a times c divided by 2 times a, 2 times 3, like that. So this gives me 8 plus minus 6, square root of 64 minus 4 times 3 times negative 7. So that is some weird number, minus 2 root 37. So this means you're going to get 2 x-intercepts. The plus minus means you have to do it twice. You're going to do 8 plus 2 root 37 divided by 6. That's going to give you one of the x-intercepts. And then you do 8 minus 2 root 37 divided by 6. That'll give you the second x-intercept. 8 plus 2 root 37 divided by 6 is going to be 3.36. 8 minus 2 root 37 divided by 6 is going to be negative 0.69. So those are our x-intercepts, 3.36 and negative 0.69. Has this made sense thus far?
Yeah.
So what are we doing? We're just trying to graph a rational function. That's the goal. We're just trying to graph it. And now what we do is we plot in all the points, and hopefully it's pretty clear of where the function is headed. So we have this, vertical asymptote is at 4, right here. There is no horizontal asymptote. The oblique asymptote is at 3x plus 4. So 1, 2, 3, 4. What's our y-intercept for this straight line? Our slope is 3, so 1, 2, 3. Go across by 1 here. Can do better. 1, 2, 3. Go across by 1 here. So this is going to be our oblique asymptote. I know what's going to happen now. It's going to be over the page. Our function is going to be over the page. So something like this, and you just keep extending it until you cross the asymptote. Something like that. So our 2x-intercepts were at 3.36, so here, and negative 0.69 here. Our y-intercept was 1.375. So here, now look at this. The only way this is gonna work, right? Look at where our x-intercepts are and the y-intercept. Remember, it has to write the asymptote. This is an oblique asymptote. This is a vertical asymptote. So it's gonna come in through here, right? It's gonna go, 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 and then it's gonna go there, and then it's gonna come right back down. And it's gonna pass through this 6%. There we go. So that's one part, right? I'm gonna check two things here. I'm gonna check for f of 5. I wanna know if I'm above or below this for 5. So I'm gonna check f of 5. So that is 3 times 25 minus 8 times 5 minus 7 divided by 1. That's 28. So I know at 5, I'm somewhere up here. So the only way this is going to work is if I write this asymptote, if I write these two asymptotes. So it's going to be something like this. Cool? And that's the sketch for this equation. And we can always double check whether we've done it right or not by using Desmo. It's such a powerful tool. We used to use a graphing calculator, which was super annoying to use. There we go. That's the sketch. And that is exactly what we have, right? 1.75, negative 0.69, 3.61, this thing. Okay, here's one last point. How do we find this? You see this vertex? What's happening there? It's turning. How do we find this and that? How do we find turning point? What's 0 there?
The slope.
The slope is 0. So for this question, if we wanted to know where the turning points were, we would find the first derivative and we would set it to 0. So to find the first derivative, you have to use the quotient rule. 6x minus 8 times x minus 4 minus f as it is times the derivative of g, which is just a 1, all over x squared. So you set this equal to 0. The denominator would disappear once you multiply both sides by a 0. Let's open these brackets. 6x squared minus 24x minus 8x plus 32 minus 3x squared plus 8x plus 7 equals 0. 8x, see you later. 3x squared minus 24x, 32 plus 7 is 39. You set that equal to 0. I'm going to quickly do it here. and we will get those two turning points. So once you set that equal to 0, you can't man it. Maybe you can, I don't know. I would use the quadratic formula. I don't like 39. I don't like odd, weird numbers. So as you can see, the two zeros are here and here, right? So that means there's a turning point at 2.268. And there is actually something went wrong. 5.37. Oh no, actually it didn't. This one is good, yeah?
Mm-hmm.
What happened here? 2.268, something went wrong with the other x-intercept. I don't know what went wrong. But anyways, you find the first derivative, set it equal to 0, that'll give you the turning points, and that's as precisely as you can graph a rational function. X-intercept, y-intercept, turning points, asymptotes. Those are the 4 things you need to graph a function as precisely as possible. Cool? All right, let's call it there for today. I'll see you next time.
Thank you.
See ya.